Yeah, thanks for the intro. Yeah, so just to repeat what he said, my name is Shoumik. I'm a fifth-year PhD student now at Stanford, and I'll talk about Weld, which is an optimizing runtime for high-performance data analytics. And this is work that I've done with my advisor, Matej Zaharia, and many collaborators. So the motivation for the Weld project is that modern data analytics applications combine many disjoint processing libraries and functions. So as an example, in the Python ecosystem, a typical data science pipeline may load some data using pandas, normalize it in some way using NumPy, and then maybe train a model or something using scikit-learn. So this is nice because on one hand, you get great results leveraging the work of thousands of authors who are implementing the state-of-the-art algorithms in each domain. But on the other hand, you don't get any optimization across these individually written and optimized functions. So how bad is it that we don't get end-to-end optimization across these independently optimized functions? Well, it turns out that the growing gap between memory access speeds and processing speeds on modern hardware actually makes this rigid function call interface to these libraries worse and worse over time. So as an example of this, here on the slide is a typical pandas program that performs some really simple data cleaning. So this program is parsing a CSV, then it's dropping some missing values, and then it's computing a mean. So each operation is actually highly optimized. So under the hood, it's implemented in C, and it's using things like SIM devectorization sometimes. But because each function executes independently over in-memory values, the overall execution is repeatedly scanning these values from main memory, and rather than collectively operating on values that reside inside the CPU caches. And because of these repeated scans over the data, even when each library is already optimized, much of the execution time can actually just go into moving data between main memory and the CPU. So together with other missed opportunities like eliminating common sub-expressions, for example, we've observed up to 30x slowdowns when combining popular libraries compared to an optimized C implementation of the same application. So there's a lot of performance left on the table with what you get using these libraries versus kind of just rolling your own solution, albeit with a lot more engineering work. So this is kind of the state of the art of data science today. Data scientists will pip install or acquire libraries that they need to perform some analysis. Then they'll observe some performance issues in pipelines composed of these fast data science tools just because they're composing them. And then they'll hire engineers or file support tickets to optimize the pipeline or to do things like leverage new hardware such as GPUs. So the vision for this project, Weld, is to basically enable this bare metal performance out of the box, even when you're kind of composing these arbitrarily already optimized libraries. So Weld's approach for achieving this is to provide a common runtime for data analytics libraries. So with Weld, libraries from different domains such as SQL or machine learning and graph processing can each submit computations to this common parallel runtime. The runtime can then analyze entire applications end to end and then JIT optimize code for each application to target different kinds of parallel hardware. So that can be multi-core CPUs, GPUs, or even future emerging accelerators. So under the hood, Weld has a number of kind of key components. The first component is this Runtime API that developers of these libraries use to actually submit computations into the runtime. The second main component is this IR, intermediate representation. So this is like a small kind of parallel programming language that Weld exposes that libraries are expected to kind of express their core algorithms in. And then the third component is an optimizer that basically takes this IR and then it takes the kind of fragments of code that these libraries submit and makes sure that they run efficiently together. So it's an optimizer that takes the IR and transforms it into kind of a more efficient version of itself. And then there's also these backends that will actually do code generation by mapping the Weld IR code into machine code for these various hardware backends. And taking this kind of end-to-end approach can actually lead to some pretty significant speedups. So this is a data set that we took from Kaggle. It's pretty simple. It's just filtering some data, computing a linear regression model, and then it's aggregating some indices at the end. And it uses NumPy and pandas. So both of these are already pretty fast. They're both backed by C. So each function is already fairly optimized. But we can kind of compare their performance when just using these libraries versus using Weld. So if we just use NumPy on pandas on a single thread, it finishes in 80 seconds. It's a pretty small workload, so it's not too bad. But allowing Weld to do its optimizations just within each library, so just optimizing the NumPy functions together and optimizing the pandas functions together already leads to an 8x speedup because you eliminate things like allocating unnecessary intermediate values and also do things like loop fusion and things like vectorization across function calls. If you allow Weld to actually optimize across libraries as well, you get a further 3x speedup. So now we're almost 30 times faster than this implementation that we started with, which is already leveraging these already optimized operators. And because of the way Weld is designed, anything you submit to it can kind of trivially be parallelized. So anything that you express in the IR, Weld will kind of know how to parallelize because of constraints that exist within the IR. So if we run this on a 12-thread CPU, we get a further speed up. So it happens to be 180x faster than the original execution in this case. So that's a huge jump in productivity when you have to wait, half a second versus 80 seconds to wait for these kinds of tasks to finish. So in the rest of this talk, I'll first discuss some details about the Runtime API. Then I'll dive into the Weld IR a little bit more. And then finally, I'll talk about Weld's optimizer. And then I'll talk about some performance results. I'll actually skip the demo because I can't see the slides up there, so it's a little hard to do. Okay, so the Runtime API uses lazy evaluation to collect work from across libraries. So this is pretty similar to APIs of other popular systems, such as Spark or Dask data frames, which also use lazy APIs. So as an example, let's say we have a user application with 3 Weld-enabled functions, right? So lib1.f1, lib2.map, and lib3.f3. When the application calls these functions, they don't actually compute anything over their inputs. Instead, each function will just use its inputs to generate a little snippet of Weld's IR to represent its computation. And then it submits these snippets and any data dependencies to Weld using this Runtime API. And then Weld will kind of internally track dependencies among individual snippets between that are submitted by these different functions. When you actually want to evaluate something, so this might be when you want to print a result or write something to disk or maybe send it over the network, Weld will actually use this dependency graph to stitch these IR fragments into a single program, and it'll lift those data dependencies up. And then it'll basically run its optimizer over the IR program and then compile it to machine code, and that's what the data in your application will actually interact with. So just to illustrate this a bit further, here's a super simple program. It's basically computing like a Euclidean distance. So it computes some squares and then a sum. But with kind of the everyday pattern that we do this, you have some data sitting around, and each function call will just kind of eagerly produce a new value. So each call is reading and writing from memory. With Weld, the Runtime API basically has this concept of a Weld object, which is basically this thing that encapsulates this DAG of dependencies. So every time you call a function, you're just registering it with this object. And that object is basically passed around to other Weld-enabled functions. So every time you call something, we register a computation. And at the end, when we actually want to see a result, we compile that into an optimized program, and we evaluate the optimized program just once. So the next kind of natural question is, how do we actually express these computations so we can actually do some optimizations over them? And this is where the Weld IR comes in. So Weld's IR is designed to meet kind of 3 high-level goals. The first goal is just generality. So we want to be able to support a diverse set of workloads, because usually these data science type pipelines are composing functions from different domains. So that might be SQL, it might be some machine learning, it might be some graph processing, for example. The second goal is the ability to basically express powerful optimizations, especially when you're kind of stitching these redundant fragments of IR together. So we want to be able to do things like loop fusion over the same data easily, but also support more hardware-specific optimizations, such as vectorization or loop tiling as well. And a lot of the design of the IR kind of goes into making these kinds of optimizations easier. And finally, we want parallelism to be an explicit concept within the IR. And this is just because modern hardware is just inherently parallel, whether it's a multi-threaded CPU or a GPU, which has thousands of hardware threads. So an IR designed for performance should kind of keep that in mind and design around it. So internally, Weld's IR is pretty small. It's kind of like a functional programming language, and it has like the usual constructs, which is branching and arithmetic, but it's kind of built around 2 main constructs. The first construct is pretty easy. It's a parallel loop. So this is just a looping operator that will iterate over your data set in parallel. But the second construct is a little bit more interesting, and it's this thing called a builder, which is a declarative object used to produce results. And when I say declarative object, that just means that a builder will say something like, I want to append items to a list, or I want to compute a sum, but it won't actually provide a implementation for how to do that within the IR. So whereas in C, you would have to say, well, I want to spawn these many threads and manage state in this particular way. The builder will just say, this is the result that I want to produce, but in the IR, it won't actually say how to do that. And the nice thing about this is that it allows for different implementations tailored to different kinds of hardware. So builders also have this additional constraint that makes parallelism easier, which says that you're only allowed to read values out of them after all writes from them are complete. And because we're kind of working in this functional world, this basically allows us to enable mutable state when implementing these builders, and also simplifies some kinds of analyses in the compiler as well. So formally, these builders are known as linear types, if you know about those. But this constraint basically exists to make compiler analysis easier. And just using these two constructs, we can capture a pretty wide variety of workloads. So we can do things like relational algebra. We can capture basically all the functional APIs of systems like Spark. We can also do things like linear and tensor algebra. And most importantly, we can also perform optimizations when you have a composition of all of these different things. So just to show an example of what the IR kind of looks like, we can implement some simple functional operators using it. So here's a map function. So this just takes a data set and a function f, and it applies f to each element in data. So the way this works in Weld is that you create this new builder. So there's a builder type in Weld called an appender. So when you do writes to it, it just appends items to a list. And when you read back from it, it gives you back that final list. And then we use this parallel for loop to iterate over data in parallel. And in the body of the for loop, we use this merge operator, which is like doing a write into the builder. And we write the value f of x into the builder. And then when we're done with that, we just call result, which will give us back the final value. So one example of how this might be implemented under the hood is that merge will kind of spawn per thread vectors and kind of tack on values onto those vectors. And when you call result, and you know result won't be called while you're kind of doing writes, you can just take those vectors and concatenate them or sort them in some way before concatenating them. So it's one reason why this writes before reads constraint makes things a little more efficient. If you want to implement reduce, it's pretty similar. We just replace the appender builder with this other one called the merger, which basically applies an associative function to anything that you merge into it. So other than that, this function looks pretty similar to the one above. Okay, so one reason that all these kind of design decisions were made was because we actually want to be able to do meaningful optimizations over the IR. And that's where this automatic optimizer comes in. So the optimizer is kind of built with two goals in mind. And these goals kind of come from Weld's setting of trying to optimize these ad hoc data science libraries. So the first goal is just to remove redundancy caused by composing independently written libraries and functions. So Weld isn't a language that you'd expect like a programmer to write. It's basically snippets of code that are kind of glued together at the end. So things like data movement or redundant traversals over the data are going to be super common, and we want the optimizer to kind of eliminate these things automatically. And the second kind of big goal is being able to generate fast code but without having to rely on external statistics. So a lot of the optimizations I'll talk about are actually similar to optimizations that exist in, say, a SQL database. But SQL databases have these nice catalogs and histograms that you can rely on to basically guide what kinds of optimizations you want to apply based on what your data looks like. But we're trying to optimize things like pandas and numpy and kind of these ad hoc libraries that people use. So we don't have access to these kinds of statistics. So we actually have an adaptive way of kind of collecting statistics at runtime and then kind of deciding which version of the code to run. So overall, the optimizer design looks something like this. We have these runtime IR fragments that are stitched together into a single combined IR program. We then apply a standard rule-based optimizer to this IR. So these rules are kind of tailored toward removing redundancy and kind of applying things that are, kind of always good to apply. So if you have like expressions that appear more than once, it'll eliminate those. And then it'll also do things that standard compilers do, just folding constants, for example. Then we have this adaptive optimizer, and it's adaptive because it'll actually insert code into your IR program that will kind of choose whether you want to run one version of the program or the other, depending on what your data at runtime looks like. So it's adaptive because it adapts to the kind of data that you're streaming through at runtime. Then you can kind of go back and run your rule-based optimizer again to fix point, or you can generate code. So we use LLVM to do CPU code generation to translate IR code into machine code. Okay, so the first category of optimizations are these redundancy removing ones. So these are rule-based optimizations that basically just pattern match on patterns in the IR and replace them with kind of more efficient subprograms. So here's a really simple kind of program. So you can think of each line in this program as being generated by a separate function. So the map call can be like an x times x in NumPy. The reduce can be like a sum in NumPy, and then again, there's like another map there. And right off the bat, we can see a number of problems with this. So we're unnecessarily kind of materializing temp, assuming that our only outputs that are of interest are sum and map. There's two traversals of data here, which isn't great because we're not exploiting things like cache locality now. And there's other things that just might be missing in the underlying implementation. So there might not be vectorization. So we might not be using SIMD vectors, for example, in the CPU. And there's also like things like, smaller things like size inference. So we don't want to keep calling malloc, for example, to grow the vector. We can kind of infer the size of the output up front. So after Weld applies its optimizations, this is what the program will look like. And it looks pretty different, and kind of the most obvious change is that we've replaced these map and reduce macros with their kind of loop and builder representation. But there's some other nice things that the optimizer has done as well. First, you can see here that we've used loop fusion to actually pipeline two loops. So this temp vector that's in the left-hand side program actually isn't materialized anywhere. We just make this merger, which remember creates aggregations, and then we merge in x times x directly instead of kind of storing it in this intermediate thing and then kind of merging it into a sum. We've also fused these two loops over data to make a single pass over the input. So in a single pass over the data, we're constructing both mapped and sum. So this is actually an optimization that is a little bit data dependent, or rather program dependent. So you can actually, there's effects like trashing the instruction cache and stuff. So it's not always worth doing this. But for simple programs, Weld will basically run like an internal cost model and decide whether it wants to do it or not. There's also some smaller things like just inferring the size of outputs to pre-allocate data. And then it also basically signaled to the backends that some of these things can be vectorized using SIMD. So there's a SIMD type in Weld, and basically adding that to the loop will say, hey, this thing is safe to kind of execute in parallel using data parallel instructions in the hardware. So there's a number of rule-based optimizations. I won't go through all of them, but many of these, as I said, kind of come from databases and compilers, but they're just nicer to apply in our IR because you don't have to worry about things like alias analysis, for example. So the second class of optimizations is these adaptive ones, and these ones come in when optimizations require data-dependent decisions. And the most classic example of this optimization is something called predication, where you might have a branch in your code and you're trying to decide whether you want to vectorize that branch at the cost of having to evaluate both branch targets. So to kind of dive into what that means, here's a simple loop. It has a branch. So if x is greater than 0, you call foo of x, and otherwise you call bar of x. So one way to possibly speed this up is to use SIMD vectors so the hardware can actually evaluate on multiple values at once. But in order to use these SIMD vectors, you need to unconditionally evaluate foo and bar, and then basically use this masking instruction in the CPU to select which ones you want to merge into your result. But if you look closely, you're actually doing more work on the right side here because you're always evaluating foo and bar. So if the branch is really predictable or it always goes one way or the other, it might not actually be worth doing this if foo and bar are really expensive, for example. So it is dependent on the data. It depends on how often x is greater than 0. So the thing that Weld does to kind of handle these cases is to basically generate code to sample the predicate and determine at runtime which iteration it should run. So it'll basically generate code like this where there's a sampling function on the input and it'll evaluate that branch condition basically to figure out how often that branch is expected to be taken. So it'll get a probability and then it'll use that probability to determine using a cost model whether it should run the predicated and vectorized code or the branched code. And a lot of this stuff again is safe to do because we have this kind of nice functional IR. So you can run this branch condition without having to worry about side effects, for example. Okay, so in terms of implementation, Weld has APIs in C, Python, Java, and Rust. So these are the languages that you can use to kind of build your own Weld-enabled libraries, and they're also the things that you can just call Weld from. We have a full LLVM-based CPU backend that automatically generates parallel code. We also have a partial NVPTX-based GPU backend. So it'll actually generate CUDA kernels and manage things like streams to offload things onto the GPU. But it only supports a subset of the language right now. In terms of implementation, it's written in around 40,000 lines of Rust with the backend and LLVM. And we have partial prototypes with pandas and NumPy, which are kind of the most fleshed out. But we also have kind of more hacky prototypes with TensorFlow and Apache Spark as well. In terms of integration effort, so how hard is this actually to use if you want to enable it in your own libraries? There's a small upfront cost to enabling Weld integration. So in our integrations, it took roughly 500 lines of code for each library we prototyped. So this is things like adding lazy evaluation into pandas and NumPy, which don't have lazy APIs, but also doing things like marshalling data between the kind of NumPy array format and the Weld array format. So these are usually 0 copies. It's just like you have to figure out where to put like the pointer that Weld can access. But it is some kind of glue code that you need to add. After that, each operator is kind of easy to port over. So I think our biggest operator was around 30 lines of code, where like there's this pandas function that performs like a weird hash join or something. So that one was around 30 lines of code. The simpler ones are like a line or 2 of code each, using the Runtime API to actually submit IR fragments into the runtime. And it's also incrementally deployable. So the Runtime API will kind of automatically figure out when it needs to convert between a Weld data type and a native library data type. So you can actually interop with native operators. So you don't have to go through and port your entire library. You can kind of focus on the most important things and kind of incrementally add more things as you need to. And if you're just an application developer, then ideally you don't really have to change anything at all. So you just import this new library and you run your code as always, and it should just work. If you want to try it out, in Python, you can pip install PyWeld. We have a subset of pandas in this package called Grizzly, which is a faster bear, apparently. And then we also have a Weldified NumPy called Weld NumPy. So those are all available on PyPy. And we also have a new release coming soon with a bunch of usability improvements as well. So look out for that for sure. So in terms of performance, so we've shown that Weld can actually accelerate several existing libraries. So in this integration we did with Spark SQL, we were able to accelerate these TPCH queries by up to 3.5x. So most of this speed up actually came from just doing native code generation and introducing things like SIMD vectorization. So Spark will already do things like pipelining and loop fusion in its Catalyst optimizer. And it also actually does code generation, albeit it generates Java bytecode and not native code. So by just generating native code that can leverage special CPU instructions, we were able to get this speed up. With NumPy, we were able to get a 4.5x speed up on one thread and a further speed up on multiple threads. So this mostly comes from eliminating things like redundant allocations of data and also fusing loops, so you don't have to unnecessarily kind of go out to memory and fetch values repeatedly. And we were actually competitive with TensorFlow's XLA compiler as well. So XLA is a compiler within TensorFlow that basically optimizes these tensor computations. So it's a similar idea to Weld, but it's kind of more tailored towards just linear algebra. So the fact that we were competitive with it, but also able to support things like joins and SQL and stuff is pretty promising. It shows that the compiler is kind of good enough to match these specialized systems as well. But Weld really shines when accelerating multi-library workflows. So this is a result I showed already, but in this data cleaning and linear algebra workload with pandas and NumPy, we were able to get 180x speed up on 12 threads, partially from parallelization, but also partially from doing things like compilation and eliminating unnecessary data movement, for example. In this workload, we are doing image whitening as a pre-processing step in NumPy, and then running a linear regression classifier in TensorFlow. So this is over images. And here, even though TensorFlow is still using this XLA compiler, we were able to get a 9x speed up because we can actually look across those library boundaries and do things like pipeline the image whitening step with the linear regression step. So instead of kind of running these as like two different phases, we looked at the whole program and compiled it down into this one really efficient kernel. And so we were able to outperform TensorFlow pretty significantly here just by taking a more global view. And then again, in Spark SQL, we were able to speed up this linear model evaluation by around 6x by basically compiling a Scala UDF to native code and kind of co-optimizing it with Spark's mapping operator. Finally, we also showed that incremental integration actually gives you incremental benefits. So this is on that Black-Scholes workload, and it's meant to show that implementing more operators will actually kind of give you incremental benefits. So it's not like implementing one operator or implementing all the operators is required to get 90% of the benefit. As you add more operators, as long as you pick the operators that are most impactful, you'll kind of get benefits slowly. This kind of points to the fact that you can take your most important operators and port them over first, and as people need them, you can add more operators as needed. So you get incremental benefits with incremental integration.
Why is it global automatically decreasing?
Sorry?
Why is it global automatically decreasing?
So you mean why does it go up at around 6? Yeah, that's a good question. So it goes up around 6 because basically the way that the operators are ported, there's some operators that are repeated. So after a point when you port some number of operators, there's an extra step of going from Weld to NumPy and back. That happens more times at that specific point. So yeah. So yeah, if you're interested, we'd also love contributors. Today we have around 30 or so contributors. We have over 2,000 GitHub stars. And there's many, many things to do, ranging from compiler optimizations to better kind of Python integration to better GPU support. So no matter what your interests are, I think there's something to do in this project. We also have contributions by others in academia and industry. So CWI is the university in Amsterdam that's kind of used it to build a new code generating database. KTH is a university in Sweden that uses it to build a new streaming system. NEC actually has this custom vector accelerator, and they used Weld to kind of target Python workloads for it. And then Databricks explored using it for Spark as well. And I also want to thank the Stanford team. This project obviously wouldn't have been possible without work from a ton of other people. So Deepak, James, Matej, Pari, Pratiksha, and Rahul were also instrumental to building this out. Yeah, so to conclude, a common runtime can speed up analytics applications by 10 to 100x on modern hardware. And this is just by kind of taking a global view and analyzing the bottlenecks on modern hardware and kind of optimizing around them by not kind of dividing your code up artificially into these function calls. So for best performance, you're going to have to kind of take an end-to-end view. And so Weld is kind of one way to do that. My contact and the code is up there. And with that, I'm happy to take questions. Thanks.
All right, thank you, Shoumik. Are there any questions? Yep.
Awesome talk. Can you compare and contrast Weld with its nearest competitors?
With its nearest competitors?
If there are any.
Yeah, so I think the one that comes to mind for most people is Numba. The biggest difference with Numba is that Weld is kind of trying to look at functions that are called dynamically and then optimize across from them. Whereas in Numba, the model is that you add this decorator over a Python function and that'll compile it for you. So it's a similar model in some sense in that we're both doing compilation and kind of looking at a lot of code at once to make it more efficient. Weld is better for these kind of dynamic settings, and Numba is better for these settings where you kind of know what you're going to run and you can kind of decorate it and just like try to get speedups that way.
Hi. Do you have any comments on what support there might be in Weld for enabling streaming and also stateful applications?
Yeah, that's a good question. So in terms of stateful applications, we've actually done some work to support that already. So the kind of execution model is that you have some code that you compile, and then you also have this other object called the context that lets you store state after a particular Weld run. So actually the way that most of our integrations work is that you feed batches of data into Weld and keep updating state in that context, and then at the end you basically run a small program that materializes the final results and pumps them out. In terms of streaming, That group at KTH I mentioned is actually working on streaming. We're not doing any active work on it, but it's something that people ask about a lot. So we're planning to kind of reach out to them and collaborate with them more. Yeah.
Have you looked into like torch integration, PyTorch integration for speeding up tensor computation?
We have, yeah. So I think one kind of way to make this easier to use is having like a nice front end for it. So people can kind of write like UDFs, for example, using Weld. So we've actually considered using Torch script to do that. So it's something we're still looking at, but definitely we've looked at it. Yeah.
Oh.
When you were comparing your product to Spark SQL, were you incorporating Scala Native at all?
With Scala Native. Was that the question? Were you recompiling with Scala Native?
Yeah, on the Spark side?
No, we were not using Scala Native. We were just comparing against Spark's kind of tungsten code generator. But that just generates Java bytecode, so it's not really native execution.
Do you support any other GPU backend other than NVIDIA?
Not currently, no.
All right. Thank you very much. We're out of time. Can we thank Shoumik again?